Okay, it looks like everybody's joined now. I apologize for the delay. I'm Sue Chrysler from Texas A&M Transportation Institute and the director of our Safety University Transportation Center here. So I'm happy to welcome you all and introduce my colleague Subasish Das, who's going to be talking about autonomous delivery vehicles. And you go ahead and put questions in the chat, or we'll have time at the end. So thanks. Go ahead, Subasish.
Thank you. Thank you, sir. Good morning, everyone. Today, I'm going to present on my safety research project, Autonomous Delivery Vehicle as a Disruptive Technology, how to shape the future with a focus on safety. So here's a team member. I'm Subasish Das. I'm an associate research scientist at TTI, and I'm the principal investigator for this project. Yanni Sapakis is the co-principal investigator, and we have several other TTI folks in the project team. Jihang Wei, a PhD student, Jackery Algard is a research engineer, Boniface Kutela, assistant research scientist at TTI, and Valerie Vaikan was basically an undergraduate student, but moved to be a graduate student throughout this project. And also we have Eric Lee from Virginia Tech Transportation Institute. So at first, the acknowledgement, I'd like to thank Dr. Sue Chrysler and Elisa Puller for their tremendous support throughout the process, and also Eric Glenn from Virginia Tech Transportation Institute for their guidance and support throughout the project activities. So here's the outline of our presentation for today. So we'll first provide some brief introduction of the automated delivery vehicle and the kind of the research gap associated with it, and project objective, the data collection effort we did for this particular project, and the analysis, and finally some recommendation and final remarks. So in the research gap, we know that that the NHTSA recently kind of grant permission to some autonomous delivery vehicles like Neuro to kind of to make their fleets available on the roads. And we know that mobility of the ADVs are limited to low-speed road. It is mostly residential locations from a nearest store. And the frequent stops and mobility among the residential neighborhood is certainly cause some safety concerns. And there is a need for comprehensive safety impact analysis and safety implication analysis to see how we can put ADV in the top of the line in all of the AV automation process. So the delivery trends of delivery vehicles has been increased a lot, and there is a significant increase after 2022 due to the COVID. But we are saying that from 2000, there is a significant increase of total retail sales that kind of increased from 6% to 12% over the year. We know that due to the kind of e-commerce economy, same day and same hour delivery has been increased a lot since 2020, and many online deliveries are now preferring same day or same hour delivery, and that is associated with more trips in the residential neighborhood. And many cities already concerned about the kind of car space uses due to the transportation network company or TNCs like Uber, Lyft, but also there is a staggering concern due to the ADVs for their frequent stop on the residential neighborhood. Here is a graphic to show that cumulative announcement of ADVs by different companies, and you see that it has started from 2015 and significantly increased till May 2020, and it has been increasing after that too. Here are some of the companies that are mostly operate automated delivery vehicles. So we list some of the companies name in a later slide. Neuro is one of the prominent leader in the automated delivery vehicles, and Amazon is another company that are making significant progress in delivering day-to-day groceries to people's doorstep. Some of the major companies are Neuro, and then we have Amazon, Gatik, Cruise, Udelf, Robomart, Third Drive, and also Google's and Waymo. They made ADV-related deliveries, but they are not particularly ADV-only companies. So after the brief introduction of ADVs and kind of the research script, here are the objective of this particular project, that what we can do in this project. So we want to explore the safety implications of ADVs. We want to determine the critical association patterns for ADV-related traffic conflicts. And then we'll develop at the end a framework, which is basically based on US DOT safe system approach for safe implementation of ADVs on the roads. The data collection effort has included 5 different data sets. We collected crash data from, or fatal crash data from FIRST. We collected data for years 2016 to 2020. We also collected data from CRSS, Crash Report Sampling System, for 5 years. And we manually collected California AV and ADV collision data from California DMV website. They provide all of the crash reports in a PDF format. And then our undergraduate student workers extracted the information and then developed a kind of spreadsheet with all of the information listed in the PDFs. And this data has been updated until at the end of 2021, and we make an open repository where we are open sourcing this critical data set. And also we collected data from Waymo. Only we are limited to the ADV-related trips, and we also collected trajectory level data, but it is a sample data for only limited trips from a third-party data vendor. To get an understanding of safety implication, we first need to understand the operational design domain of an autonomous vehicle. So autonomous vehicle has several levels, level 0 to level 5. Level 0 indicates that full human control, and level 5 indicates that full kind of self-driving control or autonomous control. And to define the levels, there is a need to see that at which level can be appropriate at what certain condition of the road. That particular framework is known as operational design domain. Many AV companies are kind of mentioning that they only need roadway marking to get the vehicle to the center line, but there are kind of guidance and policy related things are from federal agencies that will provide how the infrastructure can assist the autonomous vehicle or automated vehicles to be in the travel lane. So to define it, we need to define the operational design domain. Although operational design domain are basically controlled by OEM or original equipment maker, there are certain help can be done by the infrastructure owner operator. So all of this work, like our work, that will help or assist federal agencies to develop guidance for operational design domain at what particular condition, what autonomous level should be defined in a operating autonomous vehicle. To do that, we need to develop some use cases. So one of the use cases is that to consider how the operational design domain can be implemented in a particular framework for ADV, and then see that what are the implications we are finding. And the other way that to get some real world data, trajectory data or collision data, and to see that how these data sources can help us to develop some use cases which can be implemented in the real world. So the study is designed into 2 safety analysis. One is called safety implication analysis, another is called safety impact analysis. So in the impact analysis, we are using the ADV-related real-world data. On the other hand, in the safety implication analysis, we are kind of developing the framework that can help us to kind of create a scenario that can be replicable in a ADV-assisted roadway. So to get this implication analysis, we use 2 data sets. One is FIRST, another is CRSS. And we defined an ADV ODD definition for those two data sets, and that collected that data to see that if the ADV will be replicable there, then how the crash data will behave. So for the first, we consider light vehicles, posted speed limit less than 50 miles per hour, and non-interstate roadways and vehicles model not older than 2000 as the threshold. And similar definition is for CRSs, but you know that CRS is not only the fatal crashes, it equals both non-fatal and property damage crash too. So we kind of do the sampling in such a way that it will represent both fatal and non-fatal crashes. And the crashes we collected from 2016 to 2020, and here are the numbers from each of the datasets of all of those, these two ODD definitions. And then we define that how many collisions can occur if we consider the scenarios associated with ADV ODD. And then the vehicles involved there, and that how many defined vehicles involved in those crashes. So this data is critical because in the ADV scenario, what the companies like Neuro, they are making a point that ADV are safer because they are occupantless. So that means from the ADV side, there is no occupant. But the problem is that ADV does not have any occupant, but it moves on a road on the kind of residential locations mostly, where there are presence of lots of road users like pedestrians, bicyclists, children playing on the road, and other kind of road users like e-scooter and skating. Those sort of can happen a lot there. And if they collide with a ADV, even though ADV are very low speed, 15 miles per hour, but injury can happen. So there is a need to understand those implications from the real world crash data. So we find that if we define the data, first data, in an ODD scenario, we are distributing data that how many crashes are occurring in different roadway facility types like principal arterial, major collector, minor arterial, and local roadways. Then we are identifying that what kind of collisions are occurring there. And as a look that we for 2016 to 2020 data, we are seeing that rear end and front to rear these crashes, although in the real world data, it is showing a low representation from the first data by defining the ODD scenario. When we defined it from the real world collision data related to ADVs, and we find that rear end crashes are significantly higher compared to the FARS or CRSS data. This particular slide shows the number of occupants, and we see that single occupants are a lot in fatal crashes in the ODD scenario that defined, and there are 2 occupants and 3 and more kind of slightly lower compared to the 1 occupant. The next few slides will show the data we used. One is first ODD scenario crash data, and then second data is California ADV collisions data, and then to define some important rules from the unstructured or unsupervised data. So we used a data mining methodology to do these tasks. It is called association rules mining. So association rules mining does not have a response variable. It considers the whole data as a single matrix, and from the matrix it identified the important rules. So it identified the rules. It can be 2-item rule, it can be 3-item rule, it can be 4-item rule, but the left and right, it is known as antecedent and consequent. That means if A occurs, it is occurring with B. So that is called the rule. And the rule is associated with some performance measure. There are 3 performance measures are widely used in association rules mining. One is support, another is confidence, another is lift. Support defines how much granularity we want in the data. If we put a very small support value, then we can get the data with very few count. But if we provide a kind of 0.5 or 0.4 support value, that means that it itself indicates that we are wanting to get the rules that are occurring a little bit of higher compared to the other rules. And finally, there is one threshold or one lift, one measure, it's known as lift. It provides us information about the co-occurrence patterns in the whole data set. If the lift value is over 1, it indicates that that particular rule occurs higher compared to all other combinations in the data set. So here's an example. Like, think about that we have a collision that occurred in a curve-aligned roadway, and the collision is basically head-on, and it is at non-intersection. So if we give some numbers on these counts, we find that crash alignment curve, there are 4,852 collisions, and collisions that are head-on and intersection no that occurred nearly 1,087 times. And both of these combined together, it happens 441 times. So then we are doing the support calculations, confidence calculations, and the lift calculations to provide us the context of the whole data set. Like, for example, here, the support, when we get the occurrence compared to the whole total count, we are getting only 1% support. Our confidence is around 41%, and we find that the lift value indicates it is 2.75 based on the formula, and it indicates that it is 1.75 times higher to other combinations, that there are more head-on and intersection no and curve-related crashes can happen on those roads. So here are top 10 rules from the scenario we used from FORCE. And like the first rule we already explained in our previous slides, that it is kind of front to front, not at intersections and curve aligned. And these are the support, confidence, and rules measures. And we have a total of 320 rules from the first ADV-ODD scenario. We only provided 10 rules here to show some examples that what are the critical rules you can find in the first ODD scenario. So the top frequent items in these rules are traffic-way. It is a two-way undivided roadway, then there are 21 times of its presence. Then if it is a four-way intersection, 18 times. Traffic control signals, 16 times. Segment or not at intersections arrive at 13 times. And front to front, 13 times. And there are other variables like posted speed limit, 45 miles per hour, angle crashes, no control, and clear weather. Those are the top frequent items in the first ADV-ODD scenario. The second analysis we did, it is called impact analysis, because we are calling it impact because we gained the data from the collision data of AV-related collision data, and then we separated the data only related to the ADV-related collisions. So the rules we are finding here, that if the AV is proceeding a state and other vehicles are changing lanes, then it occurs kind of 1.5 times more compared to the other occurrence. And we provided the support, confidence, and lift value of the first 10 rules. And we collected, I think, over 250 rules for this particular scenario. And here are the occurrences, most frequent occurrences of those roads. If AV is stopped, it is 31 times. There is more chance to be occurred in a crash, and collision time rear end, it comes 31 times. And then there are other several combinations that are occurred in those top 10 rules. So after conducting the assumption rules mining using the FORCE data and California ADV data, we did analysis on some trajectory related data from Waymo and a private data vendor. From the Waymo data, we provided a simplistic analysis called jerk analysis that provides information about anomalies during the trip. So based on our finding, because it is only limited to the ADV scenario, we found that the jerk analysis is not consistent in showing significant anomalies. It is mostly due to the lower speed on those vehicles, and also kind of the limited sample size. As I mentioned earlier, that we also collected data from a third-party data vendor. So they provided us some ADV-related trajectory analysis. We tried to contact with other big ADV companies to acquire ADV-related trajectories, because that is one of the most important measure to see that during the trip, how the risk factors can be identified. But so far, the companies are still very restrictive in open sourcing their data, at least the ADV companies. So we got in contact with one of the companies, and they provided us 99 unique trips. And based on these unique trips, we defined certain thresholds, like we want to see that during the trips, how much time it is over speeding or significantly over speeding, and then hard braking. So we find that in those 99 unique trips, there are 43% of the trajectory points, they show some sort of safety critical events, either speeding or over speeding or hard braking, and it represents in the overall 6% of the total trips. So we provided detailed ranking for all of those safety critical events. In the rules are ranked based on the average scores of hard braking mean, and then provide the ranking of hard braking related ranking, and then over speeding and excessive over speeding. There are certain thresholds we used when we are defining speeding and over speeding. If the vehicle operating speed is over 1 to 3 miles, we consider it's over speeding. But if the speeding is kind of or operating speed is over 5 miles per hour, then we define this as an excessive over speeding. At the final stage of this project, we developed a decision support tool. So we know that US DOT recently adopted safe system approach. Safe system is one of the kind of methodology that was used by Sweden and Australia for at least for last 20 and 30 years. But US DOT in 2021, they adopted the safe system approach to see that how the conventional safety data analysis can be improved by using the safe system core principles and safe system pillars. And safe system core principles are based on 6 base core principles, and these core principles are death and serious injury is unacceptable, and it makes the second rule that human can make mistakes. So human cannot be focused on driving throughout the whole time. They can make mistakes, but not necessarily it means that making a mistake should be associated with serious injury or fatal crash. So our roads should be designed in such a way that it can adapt if human can also make mistake. And we need to kind of focus that human are vulnerable. We need to concentrate that responsibility is shared. One of the other critical aspect of safe system is that it is considering safety as a proactive method instead of a reactive method, like the conventional analysis we do from high safety manual and other safety analysis. It is mostly called reactive because crash occurs, then we use the observed crash, or based on the observed crash, we develop the model that have the predicted number or expected number of crashes. So it is sometimes can be defined as a reactive method, not as a proactive method. So safe system will consider the safety analysis should be in a proactive way and not in a reactive way. And also another thing to remember that redundancy is crucial. So it has 5 different pillars: safe road users, safe vehicles, safe speeds, safe roads, and post crash care. I have developed a GitHub repository by providing all safe system related recent research work, and it is updated regularly. Those who are interested to know more about safe system, please visit this link and it can give you more information about safe system and what is the current status of it. The core difference again, I think those who are in the safety research world, we know that the left side of the image that we know that driver or human are kind of responsible for around 93% of the collision patterns. That is even included in the high safety manual version 1. But the safe system approach is thinking that no, it should be designed in such a way that it is not the driver error, it is the system failure. And it is a combination of driver, vehicle, and road. And there are a little bit of certain percentage. It is kind of driver failure. It can be most probably excessive work or fatigueness or destructive nature of driving. And then sometimes it are associated with teen drivers, inexperience, and other human-related errors. The overall method is kind of important to understand that where we can implement safe system transformation. It is mostly a wider conception, but it can be considered in certain limited locations where we can consider the collective risks and personal risks. Both are at medium level to high level. If it is low level or low to medium, there are certain management processes that are already there. We can apply those methods. Again, because we'll provide a safe system related decision support matrix at the end of this project, and then that's why we are providing some brief overview of safe system, how it works with the system component, with the overall safety investigations. So here is a plot to show you that the conventional safety analysis, the graphics is taken from an UNC report, and enhanced systematic approach to road safety. So it provides how the spot, corridor, and systemic safety works, and how the safe system related analysis can work. Although they mention it is safe systems, there is a particular difference between systems approach or systems safety and safe system. Safe system is basically not necessarily a systems approach like the right hand side we provided a picture of a systems approach, and it is XMAP and all other relevant method that has a quite difference compared to the safe system approach adopted in the US DOT safe system, which was basically replicated from Australia and Sweden's safe system approach. In our project, we developed a safe system based scoring method based on the rules we identified from safety implication analysis and safety impact analysis. In our analysis, we found that rear end crash, front to front crash, autonomous mode, conventional mode, ABS stop, intersection, and other factors, these are kind of predominant in the risk factors. And we need to identify the exposure matrix here. The exposure is kind of how many ADV trips and the likelihood of crash occurrence and severity. It is defined in a out of 4 scale, which we are defining in the next slide. The scoring criteria is defined from 0 to 4. So it has basically crash likelihood and crash severity related ranking. If there is a kind of crash or near crash occurrence there, then we can score those safety scoring for particular likelihood and crash severity. And similarly, if the ADV related trip data are available, we can provide trip related exposure. And we need to ask the questions in terms of 5 pillars. It is based on safe road users, safe vehicle, post-crash care, safer roads, and safe speeds. And the questions are particularly listed here. Based on this questionnaire, we'll score all of these metrics. And then the out of 448 score, if it is a scoring very high, then there is a need to do some kind of countermeasure implementations there. And if the score is low, that means that particular road is safer for ADV-related trips. So overall, the key findings will be listed in the next few slides. But the wrap up the whole project is that we wanted to do safety impact and safety implication analysis of automated delivery vehicles on the roads. And to perform that analysis, we used 5 different data sets. We applied association rules mining on 2 data sets. We used both Waymo data and also data from an private data vendor to do the trajectory level analysis to see that how these trajectories can provide us some idea about the anomalies or kind of risk factors or how many safety critical events can happen. We found in that data that there are around kind of half of the time there are either speeding or excessive speeding on those trips. So we can tell that based on the overall finding of this project that ADVs significantly impact our economy due to the same day delivery and same hour delivery. Nowadays, there are lots of kind of ADV related or kind of delivery vehicle related tips on our local roads and residential roads, and it will increase significantly in future. So there is a need for policy related guidance to make safe travel of the roads by the ADVs. And our safety implication score shows that about 27% of the reduction can happen due to the ODD scenario, but we can expect that this kind of significant decrease may not occur because the roads will be in terms of both ADV, AV, and human-driven vehicles. The trajectory analysis from the WEMO, we found that there are minimal anomalies. On the other hand, we know that that these local road or residential roads are associated with non-vehicle or kind of vulnerable road users a lot. So there is a need for crash compatibility analysis with the vulnerable road users with the ADV in future. As ADV trips are most frequent in roadway networks with higher driver densities and non-motorist trip, it is very important for us to investigate larger scale ADV trajectory data from prominent ADV companies such as Neuro. The final remarks from this project is that we need to conduct robust trajectory analysis to identify anomalies. We already collected some data, but our data is very limited because it contains only 99 trajectories. So there is a need in future to identify anomalies and risk factors from by investigating big data kind of trajectory data analysis. And another important thing is that these ADVs are operating on the residential locations and with very limited operating speed. In many times, it has implications that other vehicles need to adapt with their low speed. So there is a more investigation needed that due to the extremely low operating speed of the ADVs on certain roads. And we also need to develop a suitable service model that goes behind beyond the current ADV service models, which are still limited to only middle mile, last mile, or final 50 feet. There may be one or two advanced studies that are doing a little bit of newer service model, but mostly are limited to basically last mile or middle mile. So there is a need in future to do more robust service model designing for this particular scenario. So with this, I'm ending my presentations. Here are my emails, and I have a website with my lab information. If anyone interested for additional questions, you can contact me. And now it is open for questions.
Okay, thanks, Subasish. Moyed's got a question. Do you want to unmute it instead of having me read it?
Can you hear me?
Yes.
Yes, yes.
Yeah, it's a great presentation, Subasish. I have a couple of questions on towards the end of your presentation on the scoring criteria. Is it only based on traffic volume or other characteristics? If you can go back to the slide and just explain a little bit more.
Yeah. A good question. So safe system-based scoring method we have developed. So if you take a look at the matrix, it has on the vertical column, we provided the crashes that can be most likely to be occurring with the ADV. And we, from our rules mining, we find that rear end crash, front to front crash, and the vehicle is either autonomous mode or conventional mode, and AV vehicle is stopping intersections. These are kind of critical factors in the ADV-related crashes, and then it is related with three performance measures, three risk factors. One is exposure, another is likelihood, another is severity. So when we are doing the exposure, so if we have the exposure data, we can count that, okay, based on the exposure, how many crashes are occurring with the rear end, front to front, autonomous mode, or conventional mode. On the other hand, likelihood and severity, it has a scoring method from 1 to 4, and that are defined in this particular table that provides that if the likelihood is less, then we provide the score 0. That's why we are saying that when we are defining that 448 scoring, if it is 0, and then if we kind of multiply it, then it becomes 0. So in terms of if the higher scoring method of out of 448, if a particular matrix, it shows that it is kind of like 20 out of 448 versus 120 out of 448, then particular roads are not safer for ADV-related trips. So we need to kind of, instead of doing the hotspot analysis, like only the observed crash, we are doing in a systematic approach that can see that either from crash or near crash data, what are the critical factors, and based on the matrix of risk factor, exposure, likelihood, and severity, how can we can score them. And to define this scoring method, we need to kind of ask the questions in the 5 pillar base, like save road users, save vehicles, and post-care, and save roads, and save speeds. And in total, the matrix with the higher value can indicate that there are more interventions are needed.
Okay. Anybody else have a question? You could raise your hand. I have a question about how can you parameterize some of the ODD features? So for instance, if I won't operate my vehicle after dark, is that something that your approach could accommodate?
Yeah, so here there is a limitation in the current analysis because we define the ODD scenario for certain measures that we have, but we can define it based on different things. Like, for example, for the current ODD scenario that we defined from the FARS and CRSs are basically light vehicle, posted speed limit less than 50, and non-interstate roadways, and vehicle models not older than 2000. That is the parameter we used for the dataset overall, both for California ADV collisions and also from FARS. But if we want to define different ODD scenario, like that dark conditions versus curve alignment as a curve, we can definitely define that scenario and come up with the newer rules. So it is possible.
Okay, good. Okay. I've put in the chat some links to the project website at the safety website, and the report will be posted there certainly within the month. It's in its final editing, and I'm sure if you contacted Dr. Das directly, he would, share the slides with you. They will be posted. You'll get an email follow-up when the recording of this is posted. I also posted a link to his GitHub site with the safe systems approach information, and a link to another safety project that pertains to autonomous delivery vehicles that you might be interested in. Okay. Hearing no other questions, I will sign off. Thanks for joining, and apologize for the late start. Thank you.
Thank you.